I will just briefly say welcome to this lecture by the Keck Institute for Space Studies. My name is Bethany Ellman. I'm a professor of planetary science at Caltech and associate director of KISS. KISS exists to bring space scientists and engineers together to advance new and revolutionary mission concepts and technologies that enable our exploration and understanding of space. We run workshops here between Caltech, JPL, external institutions. We have funding for the not only thinking, but doing in terms of the early stage technology development. And then a key part of bringing folks together is our lecture series, pulling in interesting folks who are working on hard problems, new technologies in space, and that matches our speaker today. I'm going to turn you over to Michael O'Connell, who is part of our KISS affiliates program of students and postdocs, who's going to lead you to the introduction of our speaker. So thank you for coming.
Hello, everyone. Thank you for joining us tonight, or I guess it's tonight in Pasadena. We have some people joining us all the way from the other side of the globe in New Zealand, where I'm told it's noon on Friday. So as Bethany said, I'm Michael O'Connell. I'm a member of the KISS Affiliates group. The KISS Affiliates lecture series, which this is a part of, exists to bring prominent leaders in space here to share their knowledge and experience with the Caltech community and the broader space community. So tonight we have Dr. Albert Haldemann, who is joining us from ESA. He's had a really exciting career in space. But I want to start off with the most important fact, which is that Dr. Haldemann obtained his PhD in planetary sciences from Caltech. So, Dr. Haldemann has worked in various roles. He started his career after his PhD at the Jet Propulsion Labs right here in Pasadena. And he's taken on a number of roles from engineering, science, leadership there. Before he moved to Europe, or back to Europe, I should say, to join ESA, the European Space Agency. He started doing payload assembly, integration, and verification for the ExoMars program, and he's continued doing science work there. Dr. Haldemann has a very wide range of experience working on spacecraft and science instruments. He's a space exploration enthusiast. I'm told that he's also a cyclist, enjoys dog walking and travel. The fun fact that I obtained was that he bike commutes 18 kilometers both ways to work. And although the Netherlands is flat, wind is a challenge. So don't discount that bike ride. So today, Dr. Haldemann will be discussing ESA's vision for Mars exploration. How they're merging both science and exploration objectives going forward. So please help me welcome Dr. Haldemann to the podium.
Thank you. Thank you for that introduction. And good afternoon, good day to the remote attendees. Indeed, I want to share with you some information, a little bit of PR for the other space agency, the European Space Agency. Space is our middle name, one of our logos. What I want to tell you today is sort of who we are, what we do with the European Space Agency. I'm not sure how familiar the audience is with the ESA, with ESA, and then describe in general terms what our exploration program involves and entails, and then anchor that with the story of the science-driven elements of robotic Mars exploration, which is one of the cornerstones of our exploration program, and then address in a conclusion some of the future steps and future ambitions that we have at ESA. So starting off with who we are and what we do, ESA it's not a national space agency. It is the European Space Agency. It is not congruent with the European Union. It is its own treaty-based international organization. I work for an organization that is like the WHO, World Health Organization, or the International Labor Organization. It's a treaty-based organization that is put together, it has 22 member states. It has 4 states that are sort of want to become members. And then there's also Canada is a cooperating state. Again, treaty-based organization. There are different ways to have membership and cooperation with the European Space Agency. The objective, the why, is to explore and use space for exclusively peaceful purposes. The other why is that isn't stated on the slide, but is also to, it's an industrial policy objective, which is to foster aerospace competence know-how in Europe and to achieve objectives of space exploration in doing so. We have a headquarters in Paris. We have 7 sites throughout Europe, and we operate our own launches from the spaceport in French Guiana. And we cost, this is a much smaller annual budget than NASA, something of the order 12 to 15. We did get a bit of a budget increase of 15% last November at the Ministers' Council. So we're definitely up to $7 billion a year, but that's still pretty good. You know, it's less than a movie ticket per European. What do we do? Well, you saw there that we have about 5,000 employees total. So the entire European Space Agency is about the size of that division of Caltech that is up the road that is so famous for sending robots to Mars. But we do everything. We do launchers. We do the access to space. We do enabling and support. We do the operations. We do Earth observation. We do navigation with like GPS, the European GPS system, Galileo. Telecom development and implementation, and we also do then science and exploration. So the less snazzy picture to explain that is this sort of quad chart of the 4 aspects that I mentioned. Our exploration program fits into that red upper right box, the exploration, the science and exploration program. We have a science directorate, and we have a human and robotic exploration directorate. The reason for that distinction is that our founding document states that the one thing that ESA will do is GDP-based contributions from all member states, do science missions. So there is a wedge of money that pays for science missions, and those are defined as science missions. That doesn't include directly astronauts, exploration, robotic ambitions, and space stations, and so on. So that's why we have a human exploration directorate, but it was realized you kind of need robots sometimes to work with the humans in that exploration concept, and that's evolved, and here we are. So our exploration program was called the European Exploration Envelope Program, E3P. After about 4 years, it was quickly decided that was not very catchy. So we're calling it Terrae, New Worlds. And the, again, quad chart for what we're doing is science. The exploration shall be science-driven. Scientific research, both fundamental research and exploration research, microgravity research. A lot of that is also human-related research. And economy, investments in technology, investments in industrial know-how. That's another key element. And then inspiration, motivating STEM with the kinds of projects that we enable and the kinds of information we get from the science. And then global cooperation. We're an international organization. We have to cooperate among all the member states. There's quite a bit of, well, my job as well requires quite a bit of ambassadorship, and not just from ESA to other entities like NASA, but also just within our group because we are so diverse as an organization. So that's part of what we have to do. So our exploration program is based on addressing science, economy, inspiration, and cooperation. And then there's another quad chart of how we actually then turn that into programmatics. We have 4 cornerstones. Those cornerstones are humans to low Earth orbit, humans beyond low Earth orbit, lunar robotic exploration, and Mars robotic exploration. So there are 3 destinations in that. and 4 cornerstones, 2 of them with the crewed ambitions. Those are bracketed in the red on the left-hand side. Expert, that's our technology development program, which low to medium TRL developments that then support the exploration programs, but it is a portfolio-based development. We do some basic developments that may or may not then end up in the missions, but it's nice to have that portfolio to call upon. SciSpace is the program that manages and oversees the preparation of the experiments and the scientific drivers for these exploration cornerstones. The experiments on space station that the European astronauts work on are in that program. The experiments developments heading toward that are going to be on the Artemis program are coming out of that. And then above all of that as well, recognizing that element of what we want to do, which is the industrial development, is commercialization in space. We're recognizing that's a key also geopolitical aspect, and we're paying attention to that in our programmatics. What that looks like in an infographic is a bit like this, where the light blue elements on this chart are what ESA is doing. The 3 destinations in low Earth orbit for the humans, beyond low Earth orbit for the humans with the Artemis program, where the European service module is a key component of Orion. Artemis doesn't work, Orion doesn't come back to Earth unless ESA builds the solar panels, the power, and the hydraulics, and everything that goes into that. The main engine is from NASA, fair point. But the rest, it's assembled and put together in Europe. So there's some key developments there that we're really proud of. We don't jump up and down about it quite as much. And one thing is that, you see the NASA meatball, it's free. ESA actually has on its logo, we guard it, and you have to ask our branding department if you want to use it. So it doesn't help us get the message out, but nevertheless. And then we have in light blue the things we're doing beyond that are robotic exploration, the Argonaut program, which is multiple landers to deliver payloads to the lunar surface in the multiple 100-kilogram class, and that will be part of the overall Artemis program. And the idea is that is contributing to getting European astronaut seats inside Orion for eventually landing by the end of the decade. The Mars robotic program is illustrated as well, and I'll go into that in more detail with the different elements that are there. And indeed, the aspects of that exploration program are all intended to be science-driven. We have science in each of those elements as well as the exploration. We want to learn about how humans behave in space from the human elements. And going to Mars, we're doing science-driven exploration. And I've broken that down into sort of 4 steps. The historical context, which was developed in the Science Directorate, is Mars Express as a foundation to ESA's science-driven exploration of Mars. We've elaborated on that with Trace Gas Orbiter in the ExoMars program. There's a major collaboration aspect in the Mars sample return contributions. And then we have the ambition that the other part of ExoMars, the Rosalind Franklin rover, will get to Mars this decade. And I'm going to tell you all about that. So first, foundational Mars exploration was Mars Express. We're coming up on the 20th anniversary in space of that spacecraft. It had its 19th anniversary at Mars last Christmas, and it's still working. One of the instruments is failing. We think the laser diodes on the planetary Fourier spectrometer have given up the ghost, but again, almost 20 years in space. And there's some other instruments that are a little bit flaky, but I'd say about half the payload is still working. We've done a technical assessment and decided to fund the science for at least another 3 years. And the output based on the data is pretty steady. It's about 1,500 publications, more or less, at this point, based on all that effort. Some recent results, and that'll illustrate also the fact that Mars Express had a unique orbit. It's not in a sun-synchronous orbit like the NASA orbiters. It's in a four-sol orbit where its period brings it down close to the planet, and then it has some time away from Mars where we do a lot of the data downlink. But that means it interacts with Mars at different times of day. And one of the things that allowed mechs to discover recently, the previously unnoticed annually repeating phenomenon during one particular season of orographic clouds that are tracing off of RCMONs. And basically those clouds appear, follow the atmospheric waves, but then they evaporate by about 2 in the afternoon local time where they evaporate, which is why all the orbiters that come in at 3 o'clock had never seen them before. So interesting stuff, and that's contributing to understanding regional meteorology, certain meteorological phenomena, meteorological phenomena at the planet. The the Omega infrared mapping instrument was one of it did a lot of the mapping and was kind of the first foot in the door for really mapping the clays distribution around Mars that was then nailed down by the CRISM instrument. And here's a picture illustrating the clays that Omega had mapped out in the Jezero crater where Perseverance is puttering around now. More on that later. So that's the foundation. Then the elaboration of that was with Trace Gas Orbiter, which was a cooperation at that point. It has an interesting history, and this is the history of cooperation and collaboration at ESA. ExoMars, once our member states thought, oh, ExoMars is too expensive, we were partnered with NASA in 2009. NASA said, well, we don't want to only have a lander with a rover. Our science says we need to have an orbiter to do trace gases because we've seen this interesting methane stuff. So we split the mission and had an AO, and we had 5 payloads, 1 European, 4 NASA funded, and then NASA pulled out. But we'd already let the contract for the spacecraft, so we kept going, partnered with the Russians. They put 2 instruments on board. The Belgian instrument remained, that's Nomad. The Swiss took over the camera, Cassis, and the Russians contributed an atmospheric chemistry suite and a neutron spectrometer for mapping hydrogen. And those 4 instruments, in particular Cassis, had a very fast development time, and we delivered it for its launch in 2016 from Baikonur. It has been functioning very well. It was at the time the largest spacecraft launched to Mars at 4.2 tons wet mass at launch, and it is still, as far as I know, and that record it'll probably keep for a while, the largest spacecraft to have aerobraked anywhere in the solar system with a total wingspan of 17 meters. And it was Europe's first operational aerobraking doing that, all successfully achieved. What is it for? Well, it's in the name. It's the Trace Gas Orbiter. We kept that science that it had been defined to do and that its orbit was planned to do. It has an inclined orbit at 70 degrees that is not sun synchronous, but that is designed to have as many occultations of the sun as possible. It uses the sun as the illumination source for atmospheric occultations using the 2 spectrometer suites, the atmospheric chemistry suite from the Russian Academy of Sciences and Nomad from the Belgians with other cooperating European countries. Their science teams are even bigger than that. So here's the chart. We're looking for methane. That was the key task of the Trace Gas Orbiter, and there's no methane. Now, the chart, the plot, Curiosity sees methane in the tenths of parts per billion, and those are solid detections at the surface by Curiosity, and the atmospheric column, not there. I don't know that we've really nailed down why that is, but for sure this has caused a lot of interest in the Mars atmospheric chemistry community. as well as the geochemical analysis of Mars processes that it implies are certainly something we need to know about. Also something we need to know about if we're sending humans, crewed missions to Mars eventually, one day, understanding how oxidation happens in the near surface environment, the lowest in the boundary layer, that implies quite an oxidizing environment near surface. Likewise, we have only upper limits for many of the other trace gas species that were hoped to be found. So no signatures of volcanic activity or of other trace gases that, like methane, might have been indicative of biological activity. What we have found is hydrochloric acid. There is a chlorine cycle, but it seems indeed not to be linked to any current active volcanic activity, but rather to dust and water vapor motion and cycling through the atmosphere. So this is the kind of studies that have been ongoing with Trace Gas Orbiter. They are also, we have a Trace Gas Orbiter mission extension, and they're going to be doing the D to H, deuterium to hydrogen ratios on various, and oxygen isotope ratios on various, not trace gases in this case, but on the actual major constituents, and using that to trace the dynamics of the atmosphere. So still working hard. The other instruments, the FRIEND instrument has mapped hydrogen in the near subsurface and discovered there was a neutron spectrometer on Odyssey, similar mapping, but the footprint of the FRIEND instrument is much smaller. They put in a lot of shielding to collimate essentially the detection area, so it has a smaller footprint of detectability on the surface. And with the lifetime now for the last 6 years, has got good statistics. So they've been able to reveal low latitude hydrogen-rich, probably water-rich areas, even right in the bottom of Melascasma in the canyon, so which is fairly close to the equator. So other things that we need to understand also geochemically, if there's hydrated minerals in some of those places that have been preserved. And then the camera creates beautiful pictures. Some of the backgrounds on my slides are from that as well. And that is being used to study active processes, slope lineae and polar and seasonal effects, as well as fresh craters. And we're using it for landing site characterization. For example, the slide on using it for the geologic mapping support that we did for the Oxia landing site for ExoMars Rosalind Franklin. So Trace Gas Orbiter is also key to our plans in the next 10 years because it has enough fuel for operations into the 2030s. We are taking steps to manage the reaction wheels to extend their lifetime. And we've done some software updates and so on, so it's in really good shape and seems quite likely to survive until the next slew of missions get there. It will be part of the memorandum of understanding that we'll have for Mars sample return, next story, to also offer data relay to Perseverance ongoing into the future, of course. It'll keep doing the relay. By the way, TGO does something like 60% of the data relay from Perseverance, so we're already actively contributing to my next story, which is the collaboration that is Mars sample return. So here, take a break. This just illustrates the overall architecture. The samples are procured by Perseverance, as you probably know. And then the sample retrieval lander comes to pick them up, where I'm here for the PDR that's happening this week up in the lab. And samples are, the baseline is to take the samples from Perseverance rover directly and insert them into the orbiting sample container inside the sample retrieval lander. And then one of the impossible things that JPL and Marshall and various industries need to invent is the first rocket launch from another planet. And then that orbiting sample container, that's the second stage. It's released. It's about the size of a basketball. Hopefully it's much brighter than a basketball because the Earth return orbiter that ESA is building has to find it optically at a range of 1,500 kilometers. One comparison of that is it's like seeing the clock of Big Ben from about Pisa. Another one is like seeing a 15-inch laptop screen from Pasadena if the screen is like in, not as far as Seattle, but probably somewhere up in Oregon. People were worried about stray light and stuff like that for some reason. We've had some fun with that. But why Mars sample return? This crowd has probably heard this more than once, but I'll go into it anyway for those who haven't. The Mars sample return campaign, the intent, it's responding to a scientific desire that's been around for quite a while, which is to bring samples back from Mars. It's been on 3 decadal panels, priority list, and what we have reached is we have reached not only the technological level where we collectively feel we have the technologies to do this, but also programmatically where those technologies actually match something that we can almost afford to do. So we're trying. The logic scientifically is in the middle part of the text. The oldest life preserved on Earth is about 3.5 billion years old. On Earth, it's much, much less than 1% of the surface that has rocks that are more than 3 billion years old. It's really, really hard to find that evidence for that old stuff. Mars, on the other hand, has something like half its surface that's older than 3 billion years. So Mars is likely to have a much more complete geologic record of that early part of solar system history and terrestrial planets. And we've already seen from Curiosity and Perseverance and MER before that there's habitable environments in that time period on the surface of Mars. And when you bring a sample back to Earth, you can deploy much, much more detailed and analytical tools than you can actually miniaturize and send with a spacecraft. That's why we're doing it. This is the graphic representation of the little video. This is memorable, and I show it to you because you might one day hear somebody from Mars Sample Return talk about the elephant chart. That's that. See, now you've all seen it, you're going to remember it. So the elephant chart explains it. Perseverance is the first launch. Then there's the Earth Return Orbiter in 2027. Earth Return Orbiter serves as relay support. The Sample Retrieval Lander lands. The main delivery, the red path on the top arrow, brings the samples directly from Perseverance. Should Perseverance fail, well, here's Perseverance with Ingenuity. There's the sample tube. These were the samples, and the green ones were the ones selected to put into a backup depot. So in principle, Perseverance now, that duplicate set, half of them have been put on the ground as a backup. Perseverance is going on to collect a whole lot more, and hopefully plans to deliver those 30 samples to the Sample Retrieval Lander. A key step in getting those to Earth is the sample transfer arm. That's a technology that ESA is delivering to the Sample Retrieval Lander. And we have, up till now, the robotic arms on Mars have been from JPL, the ones on, well, Polar Lander, but then Phoenix, and the arms that are on Curiosity and Perseverance, of course, and those robotic systems. But the European Space Agency just finally, after 20 years of waiting to be launched, delivered the European robotic arm to the International Space Station, where it's had some deployments and actually operational use to move a radiator on the Russian side. It's housed on the Russian side. There were many delays, not on the arm. The arm was ready to go. We had to wait for the Russians to have their elements ready. So let's see, how did I do this? And one part of that summary video I showed you that wasn't there is how the arm works. So because I'm talking to you about technology of the European Space Agency, here's how it works. You can notice there is an ESA logo on that. This is the example of the backup route. So not taking the sample directly from Perseverance, but taking the sample from the ground where one of the backup sample retrieval helicopters would have delivered it. And then it gets placed first. Pickup from the ground is a body grip pickup. So our gripper on the end of the arm, the end effector, has to be able to grip, but then also rotate in order to insert into the sample tube. It needs to hold it at the end. And it was realized that we couldn't, basically, fingernails would not be stiff enough to hold it. So we had to figure out that we could use the system that was already on Perseverance and was supposed to be dropped off, the gloves. We keep them, and we use them with the end effector to do, basically hold it at the end axially to insert it into the orbiting sample container. Then it launches, and the MAV will be the first rocket launched from another planet, and it gets retrieved by the Earth Return Orbiter. This will be, should be, the biggest spacecraft ever launched to Mars. When it goes, it will have a launch mass of 7.2 tons wet. It is a combination of chemical propulsion and electric propulsion. In order to do the round trip, it will be the first spacecraft to do a round trip to Mars. It uses the chemical propulsion to enter Mars orbit. And to give you an idea of the beast size, I mean, there's the demonstration, right? Comparing the Mars Reconnaissance Orbiter, Trace Gas Orbiter, which is the biggest one up till now, and then the Earth Return Orbiter, which is its double. Why does it need? It needs those solar panels because it needs to feed at Mars 20 kilowatts to 5 ion engines in order to be able to get back to Earth in about a year. And it needs to have it to do that. It'll use about 600 kilograms of xenon. So getting to and from Mars requires big machines. As a comparison, maybe that you're aware of, that wingspan is about the same as a 737, an Airbus 320. That's what we're talking about. That's how you get on an airplane. That's the size of that spacecraft. It's big. It will be big. It's in family with large ComSats. It's not that nobody's ever done anything that big before. It's just nobody's sent something that big to Mars before. So we're doing that. This then is the sort of a little extra illustration, but with some sort of how long it takes. The outbound transfer we are doing with electric propulsion as well. So we are taking the long way to Mars and taking 2 years to get there. We do the Mars insertion with the chemical propulsion. We jettison. We're staged spacecraft to be able to come back. We jettison that chemical stage and then have only the electric propulsion to spiral down into lower orbit, where we do telecom support, relay support with radios, UHF, and then have to locate, as I explained, the orbiting sample container. It'll be fun. Anyway, the next bit, I'm indeed having too much fun, but the next bit is the ambition. The ambition is to finish the project I was working on for so long, and that it really does have a lot of key technologies in it, the Rosalind Franklin mission. It was ready, but it was canceled because it's a cooperation with Russia, and we were 2 weeks from sending the first shipment to Baikonur when the Russians invaded Ukraine. At the end of last year, we got funding approved by our member states to develop what we had wanted to originally, but was too expensive at the time. Now the money is being ponied up by our member states, a European entry, descent, and landing module. We still need some help from NASA. We're getting sample retrieval lander engines and the radioisotope heater units for inside the rover. But all the bits and pieces of Rosalind Franklin were ready. The flight model is ready. It has some novelties like where Curiosity, Perseverance, and the other 6-wheeled NASA rovers are 6-wheel driven. They only have 4-wheel steering on the corners. We have 6-wheel steering, and we have the capability of wheel walking, which should keep us out of sand dunes and low-density drifts that might trap us like Opportunity or Spirit. Why is Rosalind Franklin still a valid thing to do even 6 years from now in 2028 with a landing in 2030? Because it has this unique 2-meter drill capability, because it has a unique integrated instrument suite, and a landing site that's unique. So still relevant. Because of the 2-meter drill, the samples and the analysis that's happened on outcrops, which by the way is already fantastic. I was there when we realized we encountered an outcrop with Opportunity. I think Bethany was as well. And realizing we were finally going to encounter a rock that was attached to the planet. But nevertheless, it's attached to the planet on Mars, where it's been exposed to UV radiation, to oxidants, and also to cosmic radiation. And what you need to do if you want to analyze anything a bit more pristine is get below about 1.5 meters. We have a drill that can do that. It's built, it's tested, and it delivers samples. And I'll just move this along a little bit because it is like watching paint dry. But it does then pull up the sample and deliver the sample. We deliver a sample into the sample holder, take an image with the close-up imager that's hosted on the drill, take an image from the mast, take it inside, ingest it, bring it to the instrument suite. There we go. So the other thing is that integrated instrument suite, where we use the remote sensing on the mast to locate the interesting geology, go and look close up. Then we have a ground penetrating radar as well. Sorry, zips. Ground penetrating radar to decide on where in the subsurface we may want to drill. I mean, of course we can drill in the near subsurface, and we will initially to test the drill, but we really want to get deep enough. And then we take the samples, crush them, bring them into a carousel where what we can do, the things that Curiosity takes samples and distributes it among instruments. We have 3 instruments in the analytical laboratory, and they all look at the same sample. So we put it into a sample holder, and there's a infrared and visible hyperspectral imager that maps it at half a millimeter resolution. And then we also have a Raman spectrometer, and so we map out the mineralogy in infrared, and then we take shots with the laser for Raman, and then shots for organic analysis with a laser desorption mass spectrometer. The Mars Organic Molecule Analyzer is really cool because it has a pyrolysis element that we can decide to use if the sample is interesting. We've only done pyrolysis on Mars so far. That bakes off lower mass organics, and Curiosity found some, but it doesn't get to the higher mass stuff, which laser desorption will get you. So first laser desorption mass spectrometer on Mars, and this is the instrument suite paper, but by the way, the 2 Russian instruments are being removed, so we'll have to write a new bunch of papers. But the other thing we're doing is we have a unique landing site. So this is the ages of the landing sites of Curiosity, Perseverance, and Rosalind Franklin. That story about seeing the early history of the solar system on the terrestrial planets, we're going to the oldest site so far, and we have the drill. So I put it to you that we have the scientific relevance and we have the technology that's ready to go do that. And that's why our member states decided they did want to make the additional investment to get us there. And here's some hot off the press, which I decided I'd show you, and maybe I'll go over time with this. Something else about the Mars Organic Molecule Analyzer instrument is that it can do 2D mass spectrometry. It can ionize with a laser desorption, pull those ions into its plasma and hold it in the vacuum, and then it can separate and split those masses in a second dimension. And when you do that, apparently, well, I'll just read what I wrote. There's a biosignature potentially called a molecular assembly parameter, and the team at Glasgow University has assessed that basically that index, When the value is greater than 15, it comes from something on Earth that was an organic molecule done by life, and numbers below that are not related to life. So we may have a quantitative biomarker that potentially, I mean, we are going to be the first 2D mass spectrometer on Mars. So if there is some biomarker to determine, credibly, we have something that could do it. That's cool, again. Future steps. This was the master plan, but of course, the real thing everybody's interested in is how do we get to that next step? People to Mars, and there's lots of difficulty in doing that. The radiation, the duration, managing the trash, sustainable space travel. That's actually something that ESA invests a lot in on ISS and so on, as do some other agencies. And then keeping your humans healthy en route. And then, of course, the launch from the return is the first step for a much smaller payload is happening with the Mars Ascent Vehicle. So we will be learning a lot. Nevertheless, we actually have written down and funded documents where we've stated to our member states, and they've agreed to this, our intention is to have sustained presence in low Earth orbit, Europeans on the moon by the end of this decade, and a vision to send Europeans to Mars in the early 2040s. And to do that, we're confronting the geopolitical reality and getting a bit more inspired that we need to have our own capability for crew and transport into space. And I think I'll just end it there. How am I doing? All right.